Hello, everybody, and welcome to our today's PCS IBS seminar. It is a great pleasure to have with us Dr. Seung-Sup Lee, and I would like to invite our scientific host, Hichul Park, to introduce our speaker. Please, Hichul.
Thanks, Tiram. Hello, everyone. Yeah. Thanks, all of the audience for coming PCS seminar. I am very pleasure to invite Dr. Seung-Sup Lee in PCS seminar. I want to briefly introduce our speaker. He got his PhD from KAIST 2013, and he stayed there same place for postdoc during for 1.5 years, and moved to Ludwig Maximilian University of Munich. Until now he's there, but he has a Humboldt Research Fellow, and he is an expert in DMFT, dynamic mean field theory, and tensor network method, for example, the numerical renormalization group and density matrix renormalization group projected entangled pair states. Today, he will give us a talk. The title is Multipoint Correlation Functions, Spectral Representation and Numerical Evaluation. Okay, let's welcome speaker. And so you can take the screen.
Okay, thank you for introduction. So I hope everybody can see my screen and I'm loud and clear. Good, so let me start. So thank you for a kind introduction. So in my talk today, I will tell you about our new method for computing multipoint correlation functions in the strongly correlated systems in a non-perturbative way. This project is a long-term collaboration with Fabian Kugler and Jan van Delft at the University of Munich, and Fabian has recently moved to join Gabi Couture's group at Rutgers University. The outcome of this project are 2 papers. The paper 1 focuses on the analytic aspect of the theory, such as generalized spectral representations of multipoint correlation functions, and shows also the numerical results of the 4-point full vertex functions. And the paper 2 explains the numerical method based on the numerical renormalization group and shows the other numerical results, such as the resonant inelastic X-ray scattering spectra. In my talk today, I will show you a subset of the results as a summary. So the goal of the project is the computation of the real frequency local 4-point functions. Why are they important? Because quantum field theory sets up a general framework for computing dynamical properties, and its basic ingredients are the 2-point functions, such as single particle propagator, or 4-point functions, such as the full vertex that encodes the information of effective interaction. Sorry, I think there is an issue. So everybody can hear me, right?
Yes, we can hear you.
Yeah, sorry. So just there was some kind of the dropout. All right. So yeah, sorry for inconvenience. So let me continue. So yeah, here the full vertex is actually can be read as the effective interaction between particles in the systems of interacting quantum particles. So also 4-point functions are experimentally relevant. So for example, non-local dynamical susceptibilities, such as magnetic structure factor, which is measured in the inelastic neutron scattering experiments, are actually quite defined by a correlation function of the spin and spin operator. So in terms of the electron operators, it becomes 4-point functions. And also the transport properties, which are defined as correlation functions of the current operators, are also again the 4-point functions in the electronic operators. Of course, one may ask, okay, isn't that an overkill, because it was just 2-point operators, but now it becomes 4-point, so it got more complicated. But actually, the reason is many solid systems are actually electronic systems. So the proper choice of the degrees of freedoms are typically the electrons, because electrons are in many cases itinerant. And also there are some other things like the consideration of the incoming and outgoing energy. So finally it ends up with the dealing with the 4-point functions. And last but not least, the inelastic scattering of photons onto the solid is also described by 4-point functions, now in terms of transition operators instead of electron operators. So in real world, experimentalists measure their data as a function of the real frequencies. So as a theorist, we should be able to compute the 4-point functions also as a function of the real frequencies. However, as we know very well from the quantum field theory textbook, the computation of the 4-point functions starting from scratch, starting from the bare propagator and the bare vertex, is very hard. In this sense, the dynamical main field theory, DMFT, and its extension theories provide a simplification. According to them, the non-local correlators of lattice systems can be obtained by considering non-perturbative local correlators of effective continuity models via field theoretical treatments, such as Bette's Arpit equation. So the problem is now reduced to the computation of local 4-point functions instead of non-local functions. But still, it is hard. Why? For 2-point functions, their spectral representations provide the relations among the spectral function and imaginary frequency Green's function and real frequency retarded Green's function. For example, from here to there, we can use the Hilbert transform, and from here to there, we can use the Kramers-Kronig relation, and between imaginary and real frequency correlators, we can use the numerical analytic continuation. However, for multipoint cases, starting from 3, 4, and so on and so forth, such relations are not known. There have been some studies on the spectral representations of the imaginary frequency correlators, but they could not be generalized. So in this regard, our achievement provides a breakthrough in the field. So our theory consists of the 2 parts. The first, we have derived generalized spectral representations of generic multipoint correlation functions. And second, we have developed the numerical renormalization group NRG method for evaluating such spectral representations. And in this talk, I'll show you the 2 sets of results. The first, local 4-point vertex function of continuity models, and the second, resonant inelastic X-ray scattering RIXS spectra. So let me start with explaining the method. So our generalized spectral representations are really generic. They can deal with any number of points, and also they can deal with either real or imaginary frequencies. And it doesn't matter whether we are dealing with local correlators or non-local correlators. In this sense, this part of our theory is more general than the later part of the numerical method. So on this slide and the later slide, I will show you some formulas. In general, I want to avoid showing too many formulas in presentations, but here what you have achieved is actually the derivation formulas. So inevitably, I should show something. So please just focus on the overall structure and the idea. Do not dwell on to the details of the formulas. So in this slide, I will show you the derivation of the L, general L point correlation function in the real frequency zero temperature formalism, which you call ZF. The correlator is defined as the expectation value of the time ordered operators. So the operators are in the Heisenberg picture, and the Hamiltonian is decomposed into the set of energy eigenstates and eigenvalues. So here we use the underlined numbers as the index of the energy eigenstates. So because there are many indices, so instead of using I, J, K, L, so on and so forth, I will use 1 under bar, 2 under bar, 3 under bar, so on and so forth. So by explicitly considering all possible permutations of the operators, we can rephrase this definition like this. So now it is sum over different permutations, and this permutation permutes the index I to the I over bar. Please don't be confused with the over bar symbols against the under bar symbols. These are for the indexes of energy eigenstates, while this I over bar is permitted from I via permutation P, and they are for the indices of the operators, time variables, and frequency variables, which will show up later on. So the according to the permutation, now it gains the sign factor plus minus 1, depending on the commuting or anti-commuting properties of the operator. And this nature of the time ordering is now given by considering this time ordering kernel, which is just the product of theta functions. So it could be visualized like this. So there is a time axis, and largest time variable is t1 over bar, and the others are sitting on its left. To obtain the correlation function on the frequency domain, now we should perform the Fourier transform. To ensure the integral converges, we should consider the convergence generating factor. For this, we temporarily fix the largest time variable and constrain the integration domain onto this half of the time axis. Then we can introduce this type of exponential factor with gamma naught positive but small, and then the integral should converge. And by using the convolution theorem, the product in the time domain becomes a convolution in the frequency domain. So here the green and the yellow term remains the same, but this blue and red terms Fourier transforms. Here the first term ensures the energy conservation. So here this dot notation is the shorthand notation implying that the frequencies with corresponding subscripts are summed up. And this red term, which is the Fourier transform of this product of theta functions, we call convolution kernel. So it is a function of the omega, the argument of the correlation function, and omega primes, which is the integration variable for the convolution, and also the argument of this blue term and the convergence factor gamma naught. So as we see, it is simply the Fourier transform of the theta function. So actually it doesn't have the information of the system itself. It rather contains the information of the formalism specific time ordering by definition. And this blue term we call partial spectral function. So it has the information now of the system and is independent from the formalism. And actually it is constructed by using the matrix elements of the operators in the basis of energy eigenstates and also of the density matrices. So you don't need to remember these formulas here. So I will get back to this point on the later slide. So the key finding of our theory is that there are three widely used formalisms in the quantum field theory. So there is ZF, which I talked about in the previous slide, and imaginary frequency Matsubara formalism, which is also widely used, and the real frequency finite temperature Keldysh formalism, again, is also widely used. So there are three formalisms, and for all these cases, the correlation functions are all given by the convolution forms with the same partial spectral functions while replacing the convolution kernels and energy conservation terms. So here the black parts remain the same and only red and the purple parts change. So there are some small differences. So first of all, for Matsubara case, the energy conservation term is defined by using Kronecker delta because in the Matsubara formalism, frequencies take the discrete value of imaginary Matsubara frequencies. On the other hand, ZF and KF is given by the Dirac delta because omegas are real variable. And for Keldysh case, now the correlator and the corresponding kernel gains now also the Keldysh indices, which they have the value of 1 or 2. That can be also read as quantum or classical. So as I showed in the previous slide, the ZF kernel looks like this. So this is the product of L-1 different terms, and each term is a linear combination of omegas, omega primes, and gamma naught. By having a finite value of this gamma naught, we can avoid divergence here. For the MF case, it has a similar shape, but it is a little bit different. So the difference is that here omega is replaced by I omega because it's imaginary frequency formalism, and here gamma naught is missing now. But of course, when we treat the bosonic frequencies, which can be 0, contrary to for many cases, then this term in the parentheses can be 0, then this part diverge. So this part of the kernel is only applied to the case when it is not vanishing. So we call this part as a regular part, and when it becomes 0, then we should use the another part which you call anomalous. It has a little bit more complicated form, but actually not that complicated. So interested audience can refer to our papers for the full expression for here. And the last but not least, the for KF case, now it is given by the linear combination of the L different kernels in the square brackets. And each term in this square bracket looks quite similar to the ZF case, but actually the difference is that now the coefficients to the convergence vectors are different. Actually, so here another key finding of our theory is that actually there are some non-trivial prefactors to the convergence generating factors. So finally, we can put this value as very small, or for analytic calculation, we can put it as a 0 plus infinitesimal number, but actually the coefficients are quite important. And also the linear combination of these kernels are given by now the Keldysh indices. So as I said, the partial spectral functions remain the same, and only the kernels change for different formalisms. So in that sense, the analytic structure of the correlation functions for different formalisms are all encoded in these kernels. So by looking at those kernels, we can figure out how the different correlators can be analytically continued from Matsubara formalism to the Keldysh or vice versa. So we figured that out, and actually for some cases, it is very simple. It is a simple replacement of the variable, changing I omega to omega or vice versa. But also there are some other more complex cases depending on the value of the Keldysh indices. And also in the numerical sense, this convolution structure indicates efficient evaluation approach. So we take this two-stage approach for computing correlation functions. First, we evaluate partial spectral functions as independent result and save it. And if we need to get some correlation functions, then we load the data and convolve them with the kernels on demand. So by doing so, actually the issue of the numerical analytic continuation is avoided, because numerical analytic continuation is actually not trivial even for simple 2-point cases. And 4-point cases, it is not known at all. And then as I showed so far, the omegas and omega primes are always come into the formula with the specific linear combinations. Actually, it comes from the nature of time ordering. I will use this property for the efficient computation of partial spectral functions on the next slide. So this is the formula which I showed in the previous slide. So it looks a bit complicated. So let me start simplification. So first, as I said, omega primes come in the specific linear combinations. I will replace the variable. And I also introduced the idea of energy dependent operator. So O of epsilon, which is energy dependent operator, its matrix element is defined by the product of the original matrix element and the direct delta function defined by using the differences of energy eigenvalues associated with these bases. So this is a schematic diagram. So left-hand side is the diagram for the original operator. So if we represent it as a matrix, so this vertical axis is for the broad space of the operator, and the horizontal axis is for the cat space. And each cell indicates the matrix element. And by introducing the energy dependence of epsilon, now these cells gain height. So the height is given by energy differences. So by using the discretized choice of the grid of the epsilons, actually we can construct this O of epsilon as explicitly high dimensional array. So I call this procedure from O to O of epsilon as slicing, because we are slicing the individual elements and assign the heights. So given that, now we can much simplify this complicated formula into this. So it has now a nested structure. Again, this is the schematic diagram for that. So the square boxes indicate the operators defining the partial spectral functions and also correlators, and the circle indicates the density matrix. This solid line with arrows indicate the contraction structure. And here it involves trace, so this line makes a loop. And this dashed line with arrow means that the argument epsilon is given by the energy difference between E of 200 bar and E of 100 bar, and epsilon 2 is given by another energy difference, so on and so forth. So it means that the epsilons indeed transition energies from formerly occupied states indexed by 100 bar, which is also associated with the density matrix, to the excited states in this indexed by 200 bar, 300 bar, so on and so forth. So it means that when we have the set of energy eigenstates and eigenvalues, we can always compute partial spectral functions. So the numerical method for such features are the numerical renormalization group, of course, and also exact diagonalization. And numerically, the treating partial spectral functions is more desirable because it has compact support. So the values of the epsilons are bounded by the largest energy scale of the system. So it cannot have arbitrarily large value. On the other hand, correlators always have long tails of 1/omega type. So it becomes quite crucial when you treat the multipoint projects in numerics, because, for example, for 4-point functions, now we should consider 3-dimensional frequency grid. And to contain the correlators within this frequency grid, then we should choose quite large grid to keep the tails of the correlators. However, for partial spectral functions, we can really choose the compact domain of the frequency space. So from now on, I will explain our numerical renormalization group NRG method that can compute the partial spectral functions for the epsilons of all magnitudes. Here, all magnitudes, I mean that it can be up to the large energy scale, which is the barrier interaction energy scale, to the very small energy scale below some emergent scale, such as the conduct temperature. NRG is the method for solving quantum impurity models. So in quantum impurity models, there is a small interacting subsystem called impurity, which is coupled to the non-interacting rest called the bath. NRG starts with discretizing the bath in an energy space on the logarithmic grid. Upon discretization, now the continuum bath becomes the collection of discretized levels. And this discretized system is mapped onto the semi-infinite type binding chain called Wilson chain. And due to logarithmic discretization, the hopping amplitudes between chain sites also scale logarithmically with the base of lambda. So we can use this property to exploit the property of energy scale separation. So we use the iterative generalization to obtain the energy eigenvalues and eigenstates of the Wilson chain. So at each iteration, we consider the part of the chain starting from the impurity to the chain site n and temporarily ignore the rest. And we diagonalize the Hamiltonian for this, and the set of energy eigenstates is called Wilson shell n. And of course, the dimension of the Wilson shell increases exponentially with n. So our computer will blow up unless we truncate the Hilbert space. So here we choose the low-lying part of the Wilson shell n and discarding the high-lying part. So we use the cap states to span the Hilbert space for a longer part of the chain, which includes the next site. And we repeat this procedure to the end. And then we can access the low energy part of the spectrum very accurately. So we can view this iterative generalization as we are zooming in to the low energy part of the spectrum of the whole Wilson chain. So it could be also read as iterative refinement of energy spectrum. So by collecting the discarded states and cap states from the calculation, actually we can construct the complete basis of approximate energy eigenstates of the whole Wilson chain. So we are now ready with energy eigenstates and eigenvalues, and we need to evaluate matrix elements of the operator to compute the partial spectral functions. For this, we also use the idea of operator expansion for efficient computation. So let's consider the operator acting on the Hilbert space of this shell n. So the vertical axis here, this is a schematic diagram for the energy spectrum associated with the broad space of the operator, and this axis is for the cat space. So as we split the Hilbert space into two parts, discarded and capped sector, we can also do the same. So we can project this operator onto the different sectors. So there are now 4 sectors, 2 times 2. So we have now 4 projections. But of course, this part is not fully refined because this kept energy sector will be further refined by considering later iterations. Then we can get the better, highly resolved result. So then we need to further split this O kept sector like this. And actually we can repeat this to the end. So by doing that, we see this kind of structure, and in terms of writing, we have this kind of expansion formula. So at each iteration, we obtain the 3 contributions representing the different projections of the operators. So basically, this idea is that we have some energy eigenstates that are actually partitioned in the different energy scales, and we are projecting the operators onto these subspaces corresponding to different energy scales. So actually, this kind of concept has been the kind of spirit of the standard energy methodology. But the actual new thing we found from this work is that we can do the same thing for the energy dependent operator. Of course, also we introduced the idea of the energy dependent operator. So with this, now we are ready to compute partial spectral functions. So we can compute it with the energy arguments as fine as possible, ranging from very large energy to the very small energies. So let me start with the simplest example of 2 points. So there are 2 operators defining the partial spectral function, A and B, and one energy argument, epsilon 1. So in the nested form, we can write like this, and we can expand the row times A and B individually over the Wilson shells. So we obtain this, and again, for each iteration, we have 3 contributions like this, except for the O kept sector, because O kept sector should be further refined by considering later iterations. So for 3-point case, now it got a bit more complicated. So there are 3 operators, A, B, and C, and 2 energy arguments, epsilon 1 and epsilon 2. So we can again expand them like this. So now we have 7 contributions from each iteration, 2 to the 3 minus 1. So there are actually 8 partitions at each iteration. So here the one box is actually hidden behind them, closer to the origin. But actually that's the O kept sector, so it should be further refined. So maybe it sounds like the end of the story. Actually, it's not. Why? Because for these 2 sectors, the result of these values of the epsilon 1 and epsilon 2 are always of the same magnitudes. However, it is possible that in the true result, correct result, one of the values can be much smaller than the other one. So to resolve this, we now use the idea of the slicing, which I introduced earlier. So I actually slice, for example, for this block. So for the some fixed cross section of the fixed value of the epsilon 1, and then we consider them as actually the space for the 2-point functions. If I fix, for example, epsilon 1, then we can consider this parenthesis as the composite operator, then it reduces to the 2-point case. So computationally, we call the 2-point routine for the computation 3-point routine as a subroutine. So also I can do the same thing for the other block. So it is a quite generic scheme. So we can actually scale up to the, for example, to the 4-point case. So for the computation of the 4-point partial spectral functions, we call the 2 or 3-point routines as some routines. So by doing that, we can gain individual resolutions of the epsilons as fine as possible. Then the rest of the job is actually the convolution of the partial spectral functions. So it inherits the resolution of partial spectral functions. So we can really resolve frequencies over many orders of magnitudes. Of course, there is one thing I want to say. So typically, in theory, we are interested in the connected correlators or vertex functions. So we are not interested in the disconnected part of correlators. So for this, we should subtract them. But actually, for numerically accurate calculations, we have developed some techniques for that, and interested audience can refer to our paper 2 for that. So far, I have explained our methods. So by using generalized spectral representations, we can treat real or imaginary frequencies on demand. And by using NRG, we can access arbitrarily low temperatures and also wide range of frequencies. And as I said, the partial spectral functions have compact support. So it is much more convenient and more efficient treating partial spectral functions numerically rather than correlation functions themselves. So to show these strengths, let me demonstrate our results. So in this talk, I will show the two subsets. And the first, I will show you our result of the 4-point vertex of quantum impurity models. As the very first result, I will show you the benchmark of Matsubara vertex in the Anderson impurity model. I believe everybody in the audience knows what the Anderson impurity model is, but let me just quickly skim through that. So there is impurity having a local repulsive interaction U, and this is just a single Fermi orbital, spinful Fermi orbital, and it is coupled to the non-interacting band with a half band with V and the energy independent hybridization strength delta. So here for simplicity, I consider the SU2 spin symmetry and also particle symmetry. I computed the vertex at impurity in so-called particle frequency convention. So U and U primes are the fermionic frequencies associated with the two particles scattering to each other, and omega is the transfer energy, which is bosonic. And sigma and sigma primes are the spins of the electrons. So because of the SU2 spin symmetry, actually there are only two independent components of this spin components. So one is the same spin, sigma and sigma primes the same. The other is the opposite, so sigma and sigma primes the opposite. So this is our numerical result. First, we have chosen the large U than delta, so it means that system is strongly coupled, and temperature is slightly higher than the Kondo temperature. And here I plot the vertex for the slice of the zero boson frequency, and to make them dimensionless, I divide by the bare interaction strength U. And I plot it as intensity plot as a function of for many frequencies U and U prime. And the first column is the different spin component, and second column is the same spin component. The first row is our energy result, and the second row is the difference between our energy result and the quantum Monte Carlo calculations provided by our colleagues in Vienna. So as we see, if we use the same range of the data, actually we don't see that much of the difference. To see the difference, actually we should crank down the range by 2 orders of magnitude. It means that our result agrees with Monte Carlo data up to 1%. So it's very good. So our method is very accurate. However, actually there are some issues. Actually, the issues of the Monte Carlo method. As we see a stronger noises. They are statistical noises, and actually those noises become much stronger outside of this frequency window. And also, the Monte Carlo calculations has trouble in reaching lower temperatures. However, our energy method can provide very accurate results even at also high frequencies. And also, it can access much lower temperatures because its computation cost scales with temperature in a logarithmic way. So in that sense, our method can outperform the state-of-the-art Monte Carlo method. So it's time to show our imaginary frequency result for the temperature much lower than the quantum temperature. Again, I show the data for the zero boson frequencies. And now I also include the insets that zooms into the lower energy window in the scale of the quantum temperature. As we see that actually there are stronger features at higher frequencies, while at the lower energies, actually there are much less features. To understand this in more detail, you have kept track down of the values of the vertex at the lowest Matsubara frequencies and change the temperature. At the highest temperature limit, the vertex takes the value of the bare vertex. So by bare vertex, it means that first, the different spin component takes the value of the U, bare interaction U, while different same spin components vanish. It vanishes because of Pauli exclusion. In the Anderson impurity model, electrons can interact only at the impurity, and due to Pauli exclusion, only the electrons of different spins can stay together. So that's why the same spin component vanishes. However, as we decrease the temperature, now the values deviate from the bare vertex value. So this is a strong correlation effect, which becomes maximal around the quantum temperature. And at much lower temperature, Now they converge to some other values. So as you know well, the elementary excitations of Anderson impurity model at temperatures much lower than quantum temperatures are described by Fermi-liquid quasi-particles. So these vertices vertex values describe their quasi-particle dynamics. So indeed, again, the same spin component vanishes, and difference of spin component is given by the ratio of the quasi-particle parameters. So first, U tilde, which is the interaction strength between the quasi-particles, and divided by the square of quasi-particle weight Z. So as we see, the quasi-particle interaction is weaker than the barrier interaction. However, by dividing by another small values, actually this ratio becomes a bit larger. Another interesting thing is actually this is another benchmark to check the accuracy of our method. So indeed, those quasi-particle parameters can be obtained from the independent calculation. So they could be extracted directly from the intractable normalization without considering the partial functions or any other things. So they agree very nicely. So this crossover of the values as a function of temperature shows the Kondo crossover from strongly interacting particles at high temperatures to the weakly interacting quasi-particles at low temperatures. So now we are ready to show the real frequency vertex. For this, I have chosen a DMFT solution of the one-band Hubbard model. Of course, we have computed real frequency vertex also in the just normal bare Anderson impurity model. For this, just you can refer to our papers. Here, I will just show you our DMFT result. So DMFT maps a one-band Hubbard model onto the Anderson impurity model with the self-consistent hybridization function. So we take a lattice site and put it as the impurity and map the rest of the lattice onto the non-interacting bath. The correlation effect within the lattice is now encoded as the energy dependence of hybridization function. So here we have chosen some simple parameters just for demonstration. So the beta lattice and also intermediate strength of the interaction. In this case, the system is in the coexistence regime. So there are two phases possible. Of course, one phase has a lower energy, but in principle, they can have both. For example, in the hysteresis way. So this is the local spectral function of the metallic solution in the coexistence regime. So it has a quasi-particle peak at the Fermi level and two Hubbard bands at high energies. So this peak explains the metallicity. The other phase is insulating phase, which has the Mach gap and only two Hubbard bands. So now we show our vertex. Again, I choose the zero Bosonian frequency slice. And here also I show only the different spin component and subtracted by the bare vertex, which is U, and divided by the U. And first column is Matsubara formalism result, and second and third are Keldysh vertices for specific Keldysh component. And the second column is the real part, and the third part is the major part. For the first row, we show the result of the metallic solution. We see that there are sign changes from here to there, red to blue, plus to minus, minus to plus, also in the major part. We found that actually this regime of the sign change coincides with the dip separating the quasi-particle peak and Hubbard band. Such sign change doesn't appear in the Matsubara frequency data. In Matsubara formalism, they are all smeared out. So it indicates that the Keldysh vertex is a better quantity to reveal the dynamics of the system. On the other hand, for the insulating case, the most of the vertex could be understood by considering just one lattice site, which is also called Hubbard atom. However, there is a very sharp and strong diagonal feature that cannot be explained by the Hubbard atom. Actually, it comes from the hybridization between the lattice sites. So it means that the body insulating phase is a collection of localized electrons, but actually they are not fully localized. They are weakly hybridized due to quantum fluctuation. Also, the quantum fluctuation actually leads to the final bandwidth of the Hubbard bands, of course. So our method and results are so accurate, so it is consistent with Fermi-liquid theory predictions, and also Keldysh vertex, real frequency vertex, reveals much richer structure than the Matsubara frequency data. As another successful application, I will show you our resonant inelastic X-ray RIXS spectra of quantum infinity systems as well. Before going into much detail, I'll explain what is the RIXS. So RIXS is photon in, photon out spectroscopy for solid systems. So let's consider an atom out of the solid. That atom has two types of the orbital. One is valence orbital forming the conduction band, and the other one is a core level deep below the Fermi level, which is typically filled. When you shine an X-ray and a photon kicks out an electron from the core level, making a core hole, and then the electron lives in the valence orbital. So this is the absorption process, the formal half of the RIXS process. The later half is re-emission process. Another electron from the valence orbital relaxes to fill the core hole, emitting a photon. The rest of the energy difference between incoming and outgoing photons are transferred to the solid, exciting many degrees of freedom. By looking at this energy dependence, we can identify what are available collective excitations in the solid systems. So RIXS has actually many experimentally powerful features, so it is a quite promising tool, but theoretical interpretation of RIXS spectra is often unclear. The reason is basically RIXS can access many degrees of freedom, and also their theoretical description is more involved. So RIXS spectra are described by the Kramers-Heisenberg formula, and in our language, actually it can be rephrased as a convolution of partial spectral function, 4-point partial spectral functions of the transition operators. So here the transition operators describe the transition from the core level to the valence orbital and vice versa. So let's start with a simpler case. If we do not keep track down of the outgoing photon energy, it is just simple X-ray absorption spectroscopy. So absorption spectrum is now given by the convolution of the 2-point partial spectral functions of, again, the transition operators. And here we have a finite core hole lifetime. So this inverse comes into the convolution form. So if this gamma p is infinitesimal, then actually the right-hand side is nothing but the imaginary part of the correlation functions of the transition operators. For RIXS case, now there are two energy differences. So incoming energy and transfer energy. Of course, we can choose another pair of incoming and outgoing energy, but to understand the fine structure of the spectrum, we choose this pair of energy, incoming and transfer energy. So this is the our rephrasing of the RIXS spectrum. And as an example, I considered the Anderson-Petit model augmented by the core level. So it is the same Anderson-Petit model, but now we included the core level, which couples to the impurity with attractive interaction. So this is the our X-ray absorption spectrum. So left panel is the linear scale plot, and right panel is log scale. As we see, we have very sharp peak. And such sharp peak is often called as X-ray at singularity. So this value of omega in 0, so actually I subtracted the some constant value to tune the peak position as 0. So here this is the absorption edge, and this absorption spectrum is mostly finite at the positive energy. And actually, this shape of the curve is given by a power law. So this exponent alpha could be explained by a so-called Hopfield rule. And this peak is in principle diverging, but is cut off by having finite core hole lifetime. Here is gamma p, or finite temperature. Here I have chosen temperature much smaller than the gamma p. So now we are ready to show the RIXS plot, but as I said, it has two energy dependencies. So to make a line plot out of them, I have chosen the maximum RIXS spectrum over the different transfer energies. So I fix omega in and choose the maximum. And as you see, we see the much stronger, larger coefficient, exponent of the spectrum. So it actually shows a very strong resonant behavior of the spectrum. Actually, it means that what is R in the name of the RIXS, resonant. So due to this very strong resonant behavior, I will now show the RIXS spectrum divided by this maximum, so which is the normalized RIXS spectrum. So as I said, there are two energy dependencies, incoming energy and outgoing energy. And this inset zooms into low energy window. To understand this in more detail, also I consider line cut for fix the omega in, and also plot the spectrum as function of transfer energy. So this dot indicates the value where the transfer energy is equal to incoming energy. So as I increase the incoming energy, also logarithmically, the peak positions moves together. You see also the dot moves together. Once the incoming energy becomes larger than the conduct temperature, then the peak starts to split. And one part of the peak moves together with the larger omega in, while the other part is pinned. Actually, this moving part, also shown as this part with the finite slope, is called fluorescence-like. This name is given based on the standard fluorescence situation that the outgoing photon energy is always fixed with this threshold value regardless of the incoming photon energy value. So the incoming and outgoing energy has a simple linear dependence of slope 1. So it is quite similar, and also in this case, so that's why it's called the fluorescence light. But of course, it is not simple fluorescence because it is a many-body system. And especially for this, for a small incoming energy case, actually the peak shapes are given by power laws. So the left part has the exponent 1, and right part is given by minus alpha, which is the same alpha from the X-ray absorption spectroscopy. So it means that actually these peak shapes are given by the itinerant quasi-particles in the conduct regime. The other part, which is pinned around the conduct temperature, also this vertical part, is called Raman-like. Again, this name is given by the standard Raman spectroscopy, where this transfer energy is always fixed to the value of the internal degrees of freedom. Of course, there is no simple internal degrees of freedom in this system because it's a many-body system. In this case, it's actually TK. To understand why such Raman-like features coming up, we have considered the limiting case of the RIXS spectra, the convolution formula which I showed in the previous slide. By taking the limit of large omega in or gamma p, actually this formula becomes proportional to the two-point partial vector functions. And now these operators are spin flip operators. And also interestingly, this partial vector functions is for the system without the core level, just normal impurity model. And this partial vector function is proportional to the imaginary part of dynamical spin susceptibility. And as we know very well, such susceptibility has a well-defined peak at TK. So basically, it means that this Raman-like peak comes from the conduct resonance in the spin susceptibility. So far, I have shown that our method can compute the low energy excitations in the presence of many-body correlations. It goes beyond the reach of existing methods, such as exact generalization that cannot access low energy excitations, or Bethel's arbitrary treatment of weakly interacting particles that cannot treat strong correlations. Here I come to the end. So there are two key messages. First, real frequency Keldysh vertex exhibits richer structure, which is invisible from the imaginary frequency Matsubara data. And we can compute the RIXS spectra for systems with strong correlations and small characteristic energies, such as the Kondo effect. As I said in the introduction, actually there are many possible applications because quantum field theory is widely used in the condensed matter theory, and many people need the accurate computation of the multipoint functions. So there are many applications, and here I list some of them. So for example, we can use the 4-point functions to describe the inelastic scattering in the mesoscopic systems such as circuit QED or quantum dots. And also within DMFT, we can compute the non-local susceptibilities such as inelastic neutron scattering spectra or vertex correlations to the transport properties. In many calculations, vertex correlations were ignored, but recently it turns out they are quite important. Last but not least, I'm quite fascinated by the possibility that we can think of the diagrammatic extensions of DMFT. It is really promising approach to study non-local strong correlations in the thermodynamic limit. To study, for example, the pseudo gap and high temperature superconductivity in Hubbard model. And they are using the multipoint functions as the input. So I think that this is one of the quite interesting applications. And again, yeah, well, there are many possible applications just yeah, out there. So I appreciate my collaborators for fruitful discussions and providing benchmark calculations. And also I acknowledge German Research Foundation for funding my independent researcher grant. Thank you very much for your attention.
Thank you, Seung-Sup, for presenting your impressive results. Let us thank our speaker. So we have time for questions. Okay, let me begin maybe. What, if you can maybe sum up, what are the approximations and kind of limitations of this whole approach, or kind of
Very good question. Yeah, so actually there is no approximation at all, but there is a limitation, of course. So here we, okay, let me start with the formal part of our theory. So generalized spectral representations. So it is very generic. So I think it could be, my hope is that later on, maybe many years later on, these spectral representations could be a part of quantum field theory textbook. So it is really generic. And the more limited part, but of course powerful part, is the numerical calculations. So we are using energy method, and it is limited to the quantum impurity systems. It means that only the small subsystems are interacting. So this is a limitation, but the calculation itself doesn't have approximation. So of course there are some numerical artifacts because it is numerical method, but it basically gives very accurate results. And then one may say, oh, it is quite limited, so it might be not that useful. But actually we have DMFT that connects the interacting lattice models with quantum impurity models. So by using DMFT, actually we can consider the interacting lattice models, as I showed here for the Hubbard model case, in terms of quantum impurity models. So in this sense, we can obtain very accurate result. And of course, again, the DMFT is also limited. So DMFT cannot treat the non-local correlations, non-local strong correlations by definition. So that's why many people have come up with extensions such as cluster extensions or diagrammatic extensions. And then of course they could be all plugged in. So, and then as I said, diagrammatic extension is really promising to treat the non-local correlations in the thermodynamic limit, because in many cases, like 2D Hubbard model or heavy formula system or many other things, actually the correlation lengths can be quite long, especially close to the phase transition. And to treat this, actually cluster extension is quite limited, because the cluster DMFT can treat only the correlations within the cluster size. However, the diagrammatic extensions can treat the very long correlation lengths. So this is quite promising approach in that regard. And for diagrammatic extensions, they are using the 3 or 4 point functions of the Anderson impurity model as the input. So we just first solve the DMFT calculation and compute the multipoint functions out of them, and we feed it to the next routine of the extension methods. Then it can construct many results. And recently there is another PRX paper having actually a lot of, it is a really big collaboration led by Thomas Schäfer in Stuttgart. Actually, he collected many people working in this business, and he compared many methods actually for the solution of the Hubbard model. And it turns out, of course, there are some numerically exact methods such as quantum Monte Carlo method, but of course their application is limited. And it turns out actually these DMFT extension methods are quite accurate compared with the Monte Carlo method. So I think in this sense, it is really a promising approach. Again, yeah, Monte Carlo methods have a problem in reaching lower temperature, or has a sign problem for finite doping. So in that sense, the Monte Carlo can provide a good benchmark, but only for the limited situations. Right, so I think this was too long answer, but I hope it helps.
Yeah, I mean, it was kind of quite general question. So
Yeah.
I think, yeah, thanks for clarification.
Mm-hmm.
We have a question from Kyungmin. Kyungmin, please ask.
Thank you for the nice talk. I have a question. Yeah, maybe you explained, but I could not get the point. What are difficulties calculating multi-point correlation functions? What are your difficulties? Yeah.
So computation cost, basically. So computation cost is higher. So as I said, here, okay, I mean, I just actually just schemed. So here actually there is a power 3. So this power 3 comes from the 4.4 minus 1. So we are doing it 4. And for 2-point case, actually is much cheaper. But actually for multi-point cases, it increases with power. Of course, this polynomial increase is actually not that huge in general, but still in the real world is not that small. So because actually this value is several tens or hundreds. So actually if we increase the number of points, actually the scales up by 20, 30 and some large numbers. So that's actually one issue, but actually all these jobs, I could get that these results from the our local cluster. Of course, our local cluster is not small.
Can you explain? So can you explain where the number 3 comes from? So yeah, I guess that it comes from the fact that there are 3 frequencies. Am I
precisely
correct
that's precise? Yeah, sure. We should resolve 3 frequencies. So we add 1 dimension basically, and then we construct a high dimensional data. So that's the reason. Yes.
Yeah. Okay. I see. So yeah, so I have another question. So can I apply your formula for optical conductivity?
Very good point. So yes, I think we can do that. Yes. Actually, also in the in my agenda. So basically, yeah, if we obtain the vertex, yeah, then we can just so we start from the local vertex because it's an impurity model. But then by solving Bethe-Zarpati equation or Parkway equation or many other things or FRG, we can actually introduce the momentum dependence onto the vertex. Then we can obtain the non-local vertex, and by using that, we can compute the conductivity. Sure, yes. But actually, this is in agenda. Actually, we have not started yet, but surely we will do. This is actually quite interesting problem. As I said, the vertex corrections actually turn out to be quite important. It is typically ignored, but for example, a recent experiment on cold atom system actually showed that even at high temperatures in the Hubbard model, actually the vertex correction is quite large, like 30% or 20%. And then actually for solid state systems, actually such temperature is above the melting temperature of cuprates. But it is very high temperature. It means that people think, okay, the correlations are not non-local, but vertex corrections are still important.
Okay, thank you.
Do we have any further questions from the audience? Let me ask maybe another one, again, more generic, but so this whole framework that you developed, it's very powerful, right, for the multi-point correlation functions, especially in respect with experiments. So have you tried already to kind of benchmark or explain some compared to some experiments on some materials, and what kind of materials kind of are you planning to tackle with this?
Yeah, so that's another very good question. So here actually, again, the issue is computation cost. Actually, this is also same for the Monte Carlo calculations. So we want to start from just one band system and so on and so forth. And actually, even before going to the lattice systems, actually, I'm planning to apply the method for mesoscopic setup. So my collaborator, okay, maybe I can show this. My collaborator suggested a setup of this in this PRL paper, for example, he suggested the circuit QED setup which models the quantum model. And there, the microwave photons are coming into the some impurity and scatters, but actually the circuit QAD systems are dissipationless. So it means that the photons should not lose energy, but actually due to interaction, they're all inelastic scattering. So the single photon coming in can split into 3 photons, for example. It is also recently measured in an experiment, also involving Moshe. And he suggested, okay, if we now can obtain the 4-point functions, actually one can theoretically compute the scattering spectra. So it doesn't involve any vertex arbitrary equation or something like that, just this direct calculation. And this is really engineered system, right? So I can just get to that point quite easily. So actually this is also in my agenda. Then the next level is actually 2D, for example, Hubbard model or some similar 1D system, one-band system. So then I will just increase the complexity. So in the long run, I want to think about, for example, what will be the outcome for the Hund metal, which is typically 3-band model, and or some heavy fermion systems, which has typically 2 bands, right? So localized and then the delocalized band. So yeah, I am thinking I will apply for I apply the method for those systems. But there's no clear benchmark weight experiments yet.
I mean, many possibilities, like you mentioned. So.
Yeah, sure. Yeah, the other issue is the computational cost. So for the realistic calculations, actually the computational cost increases for our case, because we typically use symmetries in the system, and for real systems, of course, it has much less symmetry. So that's an issue. But anyway, we are planning to do that.
Okay, thank you. Do we have any further questions from the audience? It seems not, so let us thank Seung-Sup again.
Thank you.
And with this, we conclude our